Atomic physics. My dear, this is the branch of physics that deals with the components that are made up of matter. It is divided into two. We have the one we call quantization, and another name for quantization is physics of the shell, or we call it shell physics. Then we have the second one, which we call the nuclear physics. This one discusses what happens at the shell, how there is energy quantization in electrons, the affinity of electrons, the way they get excited and de-excited. That is what we are discussing here. But on this area we have nuclear physics, which discusses what happens within the nucleus of an atom. As you learn in your chemistry, that atom is made up of two basic component parts, the shell and the nucleus. The shell contains the electrons, while the nucleus contains two basic things for your level, the proton and the neutron. Now the proton can be here, and we say it is positively charged, and the neutron, which is neutral, while the electron on its own is negatively charged. The nuclear physics studies the reaction of what is happening here and how they are being happening. Now, at any point in time, we may be, sometimes you hear people talk about, that thing is radioactive, I don't want to go close to it. It's a nuclear act, I don't want to go close to it. But the truth remains that you can even play a radioactive material as football without getting hot, unless at a particular time, which we call the half-life, and which is the next thing we're going to treat now. Half-life of a radionuclide or a radioactive material is the time taken for that particular material to disintegrate into two equal parts. If, for example, I have this, it means that in its half-life, T, it will divide into two, so that we have one part and the other part. We say that this part has disintegrated and this part is remaining. After the next half-life, we have it disintegrate again into two. After the next half-life, it will keep disintegrating that way. So we'll say that half-life is the total time taken for a material to disintegrate into its half. From there, we can give you the formula of half-life, which says that T is equal to natural log of 2 all over decay constant. The lambda here represents the decay constant, and this is my half-life. Now I can also find my decay constant by making it the subject of the formula, where we'll have my decay constant as lambda equals to into all over T. Now into is 0.63, so that we have lambda is equal to 0.632 divided by T. This is the formula for decay constant, while this is the formula for half-life, and both goes hand in hand. We talk about the fusion process. Fusion generally simply means the process or nuclear method in which two light nuclei come to join together to form a larger nucleus. For example, I have this, a small nucleus, and another one, a small nucleus, and they now come together to form a larger nucleus. This is the process of fusion. F-U, that is fusion. While we'll have the second one, which we call the fission. Fission, F-I, is the process by which now a large nucleus disintegrates into two almost equivalent or proportional nuclei. This one has to do with breaking up, while this one has to do with what? Fusing together. In fusion, two light nucleus fuse together to form a larger one, while in fission, a large nucleus disintegrates to form smaller ones. And in both of them, energy is liberated. And this can be obtained naturally or artificially. If you may know, fusion governs many natural resources of energy that we are having today. For example, in the sun, the process of energy in the sun majorly is fusion. And it has never, or in few occasions, have been obtained in the lab on Earth. Why? Because there is a peculiar problem with the process of fusion. Fusion occurs at a very high temperature of about 100 million degrees Celsius. And since there is no container to carry that, because anything that can carry such temperature will melt, and the people around are in disaster. So it is almost impossible to bring it down to the laboratory. But it occurs in nature. It occurs in the sun. It occurs in the star. We've been able to obtain it in one case or the other, somewhere in Russia, down here on Earth. But it didn't last for days and it causes disaster. But if I'm suggesting something today, I will tell all scientists, including you, my young one there, to look into this, whether there is a way we can find out something that we call cold fusion, in which fusion can occur in a lower temperature. And by that way, we have efficient and non-hazardous fusion. And as for fission, which is breaking down, there are chain reactions. So it leaves in space radioactive materials that are hazardous also to nature. Maria, let's talk about force. This is our daily language. It's either you push or you pull. That is force. Talking about force, mathematically we can say that it's the product of mass and its acceleration. Sayuri is made up of mass. When I'm moving, if I increase in velocity, acceleration comes in. So we'll say that the force of Sayuri is equal to the mass times acceleration. So this is the mathematical definition of force. Where from here we can get the SI unit, that is the main unit, as mass, which is kilogram, and acceleration, which is meter per second square. Bringing it down, we say this is kilogram meter per second square. This is the real unit of force. But the founder of this particular thing is Isaac Newton. And it is called on his name that this is equivalent to 1 Newton. But Newton cannot give you a dimension unless you resort to this. And from here we can get our dimension, where kilogram is in mass, meter in length, and second is in t raised to the power minus 2. This is the dimension of force. And there are two types of force. The first one, we have what we call the force field. And the second one, we have the contact force. Before now, we've taken an example of contact force, which is friction. You remember the lecture on friction, where I told you that friction is a contact force that acts at the boundary surface of two bodies in contact and tend to oppose the motion of one over another. But now we want to discuss about force field. Force field, these are those kind of forces that do not need any contact with anything to have influence on it. There are forces like that. Example, gravitational force. If a man is falling from 3-story building, he doesn't need a torch to start falling. That is gravitational force. Secondly, we have electric force or electrostatic force. You don't need to touch electric wire before you get shocked. Once you enter, for example, some of us do not know that. Do you know that? That if this is electric wire and it has some field around here, that once your hand enters somewhere within the field of the wire, it shocks you even though your hand has not touched the wire. Now we have magnetic force. On magnetic force, you see, even when you were a child, you bring two magnets together. When you are pulling it to the other, is either this one is running away or is getting attracted to it. They don't need to touch before you get the action. All these are force field. We have electromagnetic force, is a force field. Gravitational, electrostatic, magnetic, they are all members of force field. They don't need contact to get acting. Now I want us to take just the principle that governs gravitational force and the calculation. Then I will let you rest. as I said, gravitational force is one of those force fields that do not need a contact to have an influence on something. So from here, I would like us to discuss the law of gravity. Isaac Newton stated a law of gravitational force, and he said that for any two bodies in the universe, for example, let me have this to be body 1 and this one body 2, and these two bodies found themselves in the universe, Isaac Newton said that there is a peculiar force of attraction between 1 and 2, and that force is directly proportional to the product of mass of 1 and mass of 2, and inversely proportional to their distance apart. What am I trying to say? The law of gravitational force, we are bringing it down now to mathematics, say that force is directly proportional, the force of attraction between two bodies in the universe, even you that are sitting there and the table behind you, there is a force of attraction between two of you, that force is directly proportional to the first mass, which is your own mass, and the second mass, m2, which may be the seat you are sitting on, and then is inversely proportional to the distance, square of the distance separating those two bodies. And remember what I told you about proportionality, that is a dummy sign, that we have to remove it to bring in equality. And when equality comes in, a constant must follow to take care of that, such that we have F equal to G m1 m2 all over R. Okay, and this is the equation that governs the gravitational force as stated by Isaac Newton. Thanks very much, my dear, for listening. We've taken it all through the way, from concept of motion to conservatives, from there to waves, from there to electromagnetism, and finally atomic physics. And these are 5 books of physics. Each of them had many topics under it, but we've been able to trash all. Remain blessed and have success in your wonderful examination. UD Jesus here. Thank you very much. See you some other time.